as well as how to transform an inductor both in series, in parallel, and a capacitor in series and parallel, and what direction the current source or voltage source goes when you do that. Okay, so, and then the first problem I thought we would try a straightforward one, using both the analytical solution and the Laplace transform method. And I feel fairly certain that the one you will get on your exam, because there will certainly be one on your exam, will be something pretty straightforward like this, just a nice parallel or series RLC. And if it's not DC, like this one is DC, it'll have something that you can easily take the Laplace transform of. So let's start off by doing the analytical solution. So to do that, what do we need to do to figure out? So let me draw it on here. So we have a voltage source, which is 6 volts. We have a switch that at t equals 0. And this is 4 ohms. This is 1 Henry. And this is 1/13 farad. And I forgot to bring a calculator from my office. Okay, so what do we need to do first?
Find t equals 0 minus.
Yeah, we need to look at t equals 0 minus. Luckily, it looks like on this one, t equals 0 minus is pretty, everything should be 0.
Yeah.
Yeah, because it's not, the capacitor's not in parallel with the voltage. I don't use those.
This one?
I'd use that one before that one, but no, no. I'll go to my office if I need it, but I'll count on y'all to get the right answer. Okay, so ordinarily we'd redraw this and we'd figure out what VC of, now that one I'll use. VC of 0 minus is, and that would be 0, and IL of 0 minus would also be 0. And this is a series RLC. And if you look at the page that has the different formulas on it, we see with the series RLC, we'll be looking at the capacitor, and we'll be looking at voltage across the capacitor. So we also need to look at VC at infinity. So that we do need to pay attention to, because we're going to close the switch. So at infinity, we're going to have something else. So when we go to infinity, how do things change?
Inductor turns to wire.
Yeah.
Capacitor turns to open circuit.
Right. I wonder how I change the color on this. So the inductor changes to a straight wire, and the capacitor changes to an open circuit. So what will VC, and the switch will be closed. So what will VC at infinity be?
6 volts.
It'll be 6 volts. Okay, so we need to keep that in mind. So I'm going to clear these drawings, and we have discovered that VC at infinity is 6 volts. Okay, so the next thing we need to do is find alpha. And if you look at your page, we have 2 alphas, one for a series RLC and one for a parallel RLC. So we need the one for a series RLC, which is R over 2L. And R was 4, and L was 1. I don't think I need the calculator for this. I'm pretty sure that one is 2. Okay, so now we need to get omega. So this omega naught is 1 over the square root of LC, and it's 1 over the square root of 1 times 1/13, which is the square root of 13, which I'll just leave it like that for now, because I'll make fewer mistakes with that than with the decimal. All right, now we need to determine what type of response we have, if we have overdamped, critically damped, or underdamped. So we want to compare alpha and the square root of 13. Well, if you take the square root of 13, you'll see that that has to be somewhere between 3 and 4, because square root of 9 is 3, square root of 16 is 4. But regardless, it's bigger than 2. So alpha is less than omega naught. And with alpha less than omega naught, that means it's underdamped. Are you wondering where I'm looking, or?
I found it.
Okay. Yeah, this is on the back of the first page. And so since it's underdamped, we have to use if I change to OneNote, is it going to make my screen sharing go away? It didn't, but it didn't change to OneNote. Let's see. Does anybody know how to make Zoom stop being in whiteboard mode?
Make it do what?
Get Zoom to stop being in whiteboard mode. No, I don't know what I'm doing. Let's try this. Share. Screen. Start now. OneNote. And it went away.
Oops, I'm doing the wrong one again.
Share. Document. Nope. Well, maybe I'll try that. Document. Surface worksheet. Nope. Won't share that. All right, back to whiteboard. Share. Whiteboard. Okay. So what had we found? We had found that VC at infinity was 6 volts. We had found alpha equal to 2 and omega naught equal to the square root of 13, which told us it was underdamped. For underdamped, we have VC of t equals e to the minus alpha t times d1 cosine omega dt plus d2 sine omega dt plus VC at infinity. So we have to get this d1 and d2 and omega d. So omega d is the square root of omega naught squared minus alpha squared. D1 is VC at 0 minus VC at infinity. And D2 is 1 over C, IC of 0, plus alpha VC at 0 minus VC at infinity over omega d. So we'll start with omega d. So omega d will be the square root of omega naught squared. Omega naught is square root of 13. Square root of 13 squared is 13. Minus alpha squared. Alpha is 2. Alpha squared will be 4. So the square root of 13 minus 4, which is 9. And now my faith in leaving it as the square root of 13 is rewarded because I get omega d equals 3. All right, now I would change colors if I could, but I don't seem to be able to, so I've got the same color here. So D1 is going to equal VC at 0, which was 0, minus VC at infinity, which was 6. So D1 is negative 6. So now I have omega D is 3, D1 is negative 6, and D2 is going to be 1 over C times IC of 0, but IC of 0 was 0. So I'll just be plus 0 plus. Alpha is 2. VC at 0 was 0 minus VC at infinity was 6 over omega D, which we now know is 3. So that's negative 12 over 3 is negative 4. So I get D2 is negative 4. So now I have everything that I need. Oh, I see the problem. My Zoom panel was right on top of my Samsung panel. That's why. Okay. All right. So now I can go ahead and write my equation. So let me erase some of this up here. I'll write it right underneath the formula. And I'll write it in blue. Okay, so VC of t equals e to the minus 2t times d1 was negative 6, cosine omega d was 3t, plus d2, which was negative 4, sine of omega d, which was 3t, plus VC at infinity, which was 6. And did I do something wrong? Was I supposed to use omega d and I used...
Oh, no. Just mixing everything up.
Okay. Now, the problem said to find I of t. How do I find I of t now? I have VC of t.
F T is the same as I C of T. So C dV dt?
C dV dt. And because the circuit, which is not drawn anymore on the screen, is in series, we have the same current through everything. So IC of t is C dV dt. So make sure you have that on your formula sheet. We'll have to use the product rule here. So the derivative of e to the minus 2t is minus 2e to the minus 2t. And then I'll leave the second term alone. Minus 6 cosine 3t minus 4 sine 3t. And then the product rule says, then I take plus e to the negative 2t times the derivative of the second term, which would be 18 sine 3t minus 12 cosine 3t. And then the derivative of 6 is 0. So that should be our answer, but we can clean this up a little bit, and I want to do that so that it'll look the same as what we get with the Laplace transform. So you'll notice that I have two big terms here. The first one has a minus 2e to the minus 2t, and the second one has an e to the minus 2t. So I can factor out an e to the minus 2t out of those. So I'll do that. Oh, I forgot my c. What was c? C was 1/13. So I'll have 1/13 e to the minus 2t and minus 2 times minus 6 cosine 3t minus 4 sine t plus 18 sine 3t minus 12 cosine 3t, or 1/13 e to the minus 2t times negative 2 times 6 is 12. So I have 12 cosine 3t and minus 12 cosine 3t. So my cosines are just going to go away. And then I have 8 sine 3t and 18 sine 3t, which gets me 26 sine 3t. And lo and behold, 26 divided by 13 is 2. I get 2e to the minus 2t sine 3t. That kind of lets you know you probably did it right if you get such a pretty answer like that, because this is like the cleanest RLC problem I've ever seen. So our Laplace transform should work out nicely. So that would be our answer, and that would be in amps. And that's lowercase I of t because it is in the time domain. Let me see if that is actually the right answer. Two e to the negative 2t sine of 3t u of t. Yeah, I do need a u of t because there was the switch that started at t equals 0. I always forget my u of t. Tell me when y'all are ready.
So this is going to be probably the main biggest problem with the exam.
Probably. Because your last test covered, did you have RL and RC circuits on the last test?
She's going to put one problem from chapter 6 and one problem from chapter 7. She's forcing us to do one with these and then one with Laplace transform.
Yeah. So that's probably, yeah. So this and then what I'm about to do with Laplace transforms. And I would expect that, again, that, she's not going to do one that's as complicated. I still need to do this one with Laplace transforms. The other two in this handout are pretty messy, and so I probably will do them in videos. I don't know if we'll get to them today. All right, so now let's do the same one with Laplace transforms. So I've got 6 volts and 4 ohms, 1 Henry, and 1/13 farad. So first I need to go to the S domain. So to transform a DC source to the S domain, anytime you just have a number, the Laplace transform of the Laplace transform of 1 is 1 over S. And multiplying by a constant doesn't change anything. So the voltage source becomes 6 over S. And then once you transform things to the S domain, they become impedances and they all act like resistors. You can add everything like a resistor. So resistors, as a matter of fact, they're our favorites. They don't ever change. They're just 4 ohms. And all impedances are in ohms. Now, to convert an inductor turns into L times S, with a voltage source equal to Li naught. And so our inductor will be 1S. And I would put in a voltage source here if I had had any current at t equals 0, but I didn't. So I'm just going to leave it out. And then a capacitor transforms to 1 over SC, and V naught over S is that voltage source. You'll notice that the orientation, the polarity of the voltage sources is different for an inductor and a capacitor. So that's something to pay attention to. But in our instance, V naught of 0 was 0, so again, we don't have that. And so this will become 1 over SC. So 1 over 13 is 13. So this becomes 13 over S.
Makes it easy.
Yes. Okay, so now once you have it in the S domain, you can use everything you learned in chapters 2 and 3 in circuits 1 of voltage division and Ohm's law and nodal analysis and mesh analysis. All of that works, and you treat all of your elements just like you would treat resistors. And so these are in series, and so they add. So I can say that V equals I Z. Z is the symbol for impedances. It's just like R, but it's just saying, well, they're not really resistors anymore. And so 6 over S equals I, and I'm using this capital I to indicate that I'm not in the time domain. This is I of S. This is I of this function S. And then my total impedance will be 4 plus S plus 13 over S. And then my next step is to get I by itself. Now, in this problem, it worked out really nicely that I didn't even have to factor the I out. Usually you have to factor it out. This time it was already factored out. So I can say I equals 6 over S times 4 plus S plus 13 over S. Well, that's not in the right format. And so I'm going to need to get it into the right format. Unfortunately, I think I can do this. Do y'all have this written down?
Mm-hmm.
Okay. So can y'all tell me what I just had?
6 over S times 4 plus S plus 13 over S.
Okay, so I need to multiply this by S over S. So when I do that, actually, I don't need to do that. I lied. I don't need to do that. I need to multiply this S in the denominator through, and that'll take care of my denominator here. So I have 4S plus S squared plus 13. And now let's get that in good factoring order. S squared plus 4S plus 13. Now, if my S squared had a coefficient, I would have to factor that out of everything. And we can see that what I have is not something that nicely factors. If it did nicely factor, my answer would be exponential, but I already know my answer. It was sine, right? So that lets me know that I've got a complex number here. And if you think back to your differential equations class, what I want to do is complete the square. So I take half of 4, which is 2, and I square it, and I get 4. So I add 4, and then I subtract 4, so that I didn't really just add 4 out of nowhere. I really added 0. And now I can write this as s plus 2 squared plus, that's 9, which I already know is 3 squared. And then when I look at my table of Laplace transforms, I see that the one that has s squared plus omega squared in the denominator has an omega on the top. Now, the plus 2 means it's a shift. It's a time shift, which is not in this table. Oh, no, it is. No, oh, we have it. We have it e to the minus at. So we have in the table I gave you, we have omega over s plus a squared plus omega squared. That's almost the format that we have right here. It's just omega is 3. So I need to have a 3 on the top. So I can easily get that by writing this as 2 times 3 over s plus 2 squared plus 3 squared. Now it looks exactly like this, which is in my table of Laplace transforms. If you don't have and actually I don't think the one from your book has it written like this, or, oh, it does? Oh, okay, so you have that already. Okay, so then I can say that this is, well, that's I of s. So now I can take the inverse Laplace transform, and I can say I of t equals 2 times, and this said that this was the Laplace transform of e to the minus at sine of omega t. So in mine, a is 2 and omega is 3. So this would be 2 times e to the minus 2t sine of 3t.
It's interesting that those values are the same in both equations, the alpha and the omega.
Yeah, it's actually not a coincidence because they actually have the same meaning. So it's like when you see that, you think, okay, maybe I'm doing something right, because it actually is an omega. It actually does have some relevance. I'd love to be able to tell you exactly why, but I don't have that.
I don't understand.
Okay, so at this point, I'm going to stop this recording.